Okay, so here is our next example on biconverter. Okay, so far we've covered about 2 examples. Yeah, so I'm mainly focusing on solving those example problems. Okay, just like I promised, I'm going to make another video where I'll just focus on explaining the concept of back converters, boost converters, and back boost converters. Okay, but in these examples, I'll just be focusing on solving the problem. Okay, so let's get started. So we have a question here. The question says a back converter is supplied by a DC source of 48 volts. It produces an output voltage of 18 volts across a 10 ohm load resistor. Assume that the capacitor is large enough so that the output voltage is kept constant. Determine the duty cycle, okay? The minimum inductor size, Lmin, if the switch frequency is 40 kilohertz, okay? And we have so many questions coming. Okay, so let's list the data that is provided to us. So we are given a couple of things. We are given the source voltage. Remember that the back converter steps down the DC voltage, right? Okay, so we're given the source voltage. We are stepping down 48 volts. So V source equal to 48 volts. Okay, we are given the output voltage. So we have stepped down 48 volts to 18 volts. Okay. Okay, so we have connected the load, okay, of that resistance, 10 ohms. Okay, so remember that the voltage is taken across the capacitor. The function of the capacitor is just to maintain the constant voltage across the output terminals. Okay, so the first part of the question says you have to find the duty cycle. Just a reminder, remember how the back converter looks. Okay, you have a DC source. Okay, you have a DC source here, and then you have a switch. Okay, this position. Okay, and then have a diode. Have an inductor. The capacitor. Okay, and then we have the load connected here. Okay, so this will collect the output. So as you can see, the capacitor is connected in parallel with the load. Okay, so this capacitor, the voltage across the capacitor is 4 volts, even the voltage across the load will be 12 volts. Okay, so we have the inductor here, we have the switch, we have the supply voltage. Okay, and then we have the diode here. So you notice that if this switch is closed, okay, when the switch is closed, we are going to have a short circuit here when the switch is closed. Okay, so when the switch is closed here, what will happen is that this side of the diode is connected to the positive terminal. This side is going to the negative terminal. So what will happen is that the diode will be in reverse bias, right? Okay, so you have a diode in reverse bias. So we represent that with an open circuit. Okay, so we have an open circuit here. So meaning there's no current flowing through the diode. So the current will just flow from the source to the load, right? Okay, to the load, assuming that okay, no current flows through the capacitor, of course, steady state conditions. So the inductor is going to charge in this manner, right? Okay, so when the switch is closed, the inductor will charge, right? Okay, remember that the inductor acts as a energy storage element in the circuit, right? When charges stores some energy, so it's going to charge this polarity. Okay, so when the switch is open, okay, when the switch is open, if you try to open the switch, what is going to happen is that, let me just bring back the diode, right? Okay, so the picture of the diode is going to look like this, right? Okay, so I've opened the switch. Okay, so what will happen is that the inductor, according to its properties of an inductor, it's going to reverse the polarities, right? According to Lenz's law, isn't it? Okay, so the polarity will reverse. So as you can see, this diode now, okay, with respect to an inductor, which is the energy source, of course, the diode is connected to the positive terminal, right? Okay, so it's a positive terminal with respect to an inductor. Or I mean, the anode is connected to the positive terminal. The cathode is connected to the what? To the negative terminal. So the diode is forward biased, right? Okay, so the diode is forward biased in this case. And now you've disconnected the main source, isn't it? So what is supplying energy to the circuit now is just an inductor itself. And you know that as the time goes to infinity, right? During the steady state condition, this inductor is going to discharge all its energy through the load, isn't it? Okay, so the current in the inductor will eventually reduce, right? Okay, so this is how the circuit behaves. So when the switch is closed, the inductor charges. Okay, the inductor charges, and then when the switch is open, the energy stored in an inductor is discharged through the what? The load. All right. Okay. So now you see that the energy through the inductor, okay, will be less as compared to the what? To the energy that is this stored in the supply, right? Okay, I mean that the energy that is supplied, isn't it? So as a result, you find that the output voltage will be smaller as compared to the input voltage. Okay, but I'll show in the other video mathematically how you can get the relationship between the input voltage and the output voltage. In this video, I'm mainly focusing on doing the calculations. Okay. So let me just remove the circuit. Okay, so question number one. Number one is asking us to find the duty cycle. And for us to find the duty cycle, we need to know the relationship between what? The output voltage and the input voltage for a buck converter. And I think I explained this one here in the previous video. Okay, here, where is that? For a buck converter. Okay, here's the equation, right? For a buck converter. Okay, so that's the relation between the voltage output and the input voltage. Okay, so the output voltage is always less than the input voltage. So from this, you can find the duty cycle. So the duty cycle will just be equal to the output voltage divided by the input voltage. Okay, so the output voltage, remember, was 18 volts. Okay, 18 volts. The input voltage is 48 volts, and if you divide the two, you get the duty cycle of 0.375, right? Okay, or we can put it in percentage as at 7.5%. Okay, so this means that 35.7% of the time period of the signal is in the on state. The remaining percentage is in the what? In the off state. Okay, so the signal is in the off state, which is about 62.5%. It's off. 37.5% is on. Okay, so that's for part one. Part two, we need to calculate. What? The minimum inductor size. Okay, if the switching frequency is 40 kilohertz. Okay, so this one I wish I could show how to drive. Now because of the limited time, I'll just state the formula, right? Okay, so for the minimum inductance, we're going to use the formula here. So Lmin. So the minimum inductors we need to connect in the circuit so that there is continuous supply of current. Okay, there's no discontinuity. Okay, the current across the load is continuous. Okay, so this is the formula you need to use, right? The resistor minus duty cycle times T divided by 2, right? Okay, so this one can also be written as what? R1 minus D over 2F, right? Okay, because know that period T is equal to 1 over frequency. Okay, so let's substitute the parameters that are given. So Lmin, the resistance, okay, so from the question we told that the load resistance is 10 ohms. Okay, so of 10 ohms. The duty cycle, we calculated duty cycle as 0.375 divided by twice the frequency, right? Okay, so what's the switching frequency? Okay, are we given the frequency? Oh, we are given that the frequency is actually 40 kilohertz, right? Okay, so the switch we are like operating a switch at 40 kilohertz, and of course the switch is not the mechanical switch that we know. Okay, it's actually an electronic switch, which is a transistor. Okay, so you see the frequency, how many times it's been switched on and off per second, right? So 40,000 times, which is 40 kilohertz. Okay, no one can manage to do this. Can you switch on and off the mechanical switch 40,000 times per second? No. So the one electronic component that can do this is transistor. Okay, transistors are switching elements with very high frequency. They can switch circuits at very high frequency. Okay, so we use the transistors. Okay, so and if you plug in the value, you calculate everything here, you find that the minimum inductance is about 0.000078125 Henry, and you can convert this to smaller units, which is 78.125 microhenry. Okay, so this is the minimum inductance that we need to connect in the circuit so that you can ensure that there is a continuous supply of current across the load. Okay. Okay, so that's the end of question 2. Question 3 says we need to calculate the inductor current. Okay, if L is equal to 1.25, okay, times Lmin. Okay, so we need to find it. So we are told that, okay, the actual inductance that we're using now is L, which is 1.25 times the minimum inductance. So in this circuit, we are using the inductance of that much. So first, let's find L itself. Okay, so I told that L is equal to 1.25 times Lmin, right? Okay, so we are just from calculating the minimum inductance, so we can substitute. Okay, so 1.25 times Lmin. So Lmin is simply 78.125 microhenry, right? Okay, and if you calculate the inductance in the circuit, we found that the inductance is about 97.656 microhenry. Okay, so that's the inductance. And then now from this, we can now find the current, the inductance current. So there are two types, right? Okay, there are two portions. Okay, so after time period t, right? Okay, so what happens is that when the switch is closed, right? When the switch is closed, the inductor will charge, right? Okay, up to some point here. Okay, so during this time is when the switch is closed, right? So this time here is a duty cycle times a time period, right? Okay, and then when the switch is opened, you saw from the circuit that when the switch is open, the inductor becomes the source, so it discharges, right? Okay, until the next time period. Now, if this inductor is not large enough, it won't be able to discharge during this whole time. Okay, so this time is what? 1 minus d times t. Okay, during that time when the switch is off, this inductor has to be able to supply the current until the next time period, and then it continues just like that, right? So that's how the waveform looks like, right? Okay, so no wonder it's important for us to size this inductor, how big it's supposed to be, so that the current is continuous. We don't have a situation whereby the current like just doing that off state. We find that the current is so small, like I mean the voltage stored in the inductor is so small so that it can't manage to supply the current in the circuit during the whole time period when the switch is off. Okay, so we are trying to avoid this situation whereby you have this kind of waveform, right? So you end up having this kind of waveform if the inductor is not large enough, right? Okay, so that's what I mean continuous current. Okay, so that you are able to supply, okay, during this time, and then just like that. So at this point here, this current here, okay, remember it's not going up to 0, right? Okay, stops at some point. This current is called the Imin, the minimum current, okay? And then the maximum current is this current here, Imax. Okay, so I'll drive these equations later on, okay, but not in this video, of course. So you notice that during this on state, the inductor current increases, right, linearly. Okay, this is more like a linear relationship, isn't it? Okay, so the inductor current increases during that period, right? Okay, so we have a positive slope, right? And then during the off state, when the switch is closed, so when the switch is open, you find that the current in the inductor is decreasing, means that the inductor now is discharging, okay, through the load, right? And then during another time period again, okay, after another cycle, you find that again the current increases in the inductor, then decreases, just like that. So that's how the waveform looks, right? Okay, so we need to find those currents. Okay, so the first current you're going to have is from 0 to d times t, this time period here. Okay, so it's from 0, okay, to dt, right? And then another portion of current is be this one here, discharging, right, from dt to t, right? So we need to have these two piecewise equations, right? Okay, piecewise functions. Okay, so let me just clear this. All right, so I'll start, right? For what time period? From 0 to duty cycle times time period, right? Okay, yeah. So the formula is given as follows, okay? So the formula is given as the inductor current IL of t, okay, is equal to, okay, the supply voltage minus the output voltage divided by the inductance itself, okay, times t, sorry, times time period, right? And then plus Imin, okay? Imin is more like the y-intercept, okay? I showed you this, the Imin, right? It's a y-intercept. So Vs minus Vo over L is simply what? The slope of this equation, isn't it? So you know that Vs and Vo, Vs is greater than Vo, so it's positive, isn't it? Okay, so this slope is actually positive. So no wonder you have this kind of equation or line, right? Okay, so we need to find Imin first, right? We have Vs, or Vo, we have L, we have everything. So Imin is equal to, okay, so remember that for the back converter, Imin we calculate like this, Vo 1 over R minus 1 minus duty cycle, okay, divided by 2L times frequency, right? Okay, so we have all this, okay? We have the output voltage, okay, which is 18 volts, of course, 18 volts with the output voltage, okay? And then we have resistance, which is, what was the resistance? Okay, 10 ohms, okay? We have the resistance of 10 ohms, of course, okay? And then we have, we also have minus 1 minus duty cycle, duty cycle, and then this is a duty cycle. So please have that. So duty cycle, okay, 0.375. Okay, and then we also 2 times the inductance, it's 97.565 microhenry times 10 to the negative 6, and then times frequency 40,000 hertz, right? Okay, so if you calculate properly this, we're getting the value of about I mean is about 0.36 amps. Okay, so I mean of about 0.6 amps, right? So now we can plug those values in the equation. So we have the inductor current is equal to 48 Vs, and then Vo 18, okay, divided by inductance, which is 97.565 times 10 to the power negative 6, okay, and then times t, okay, times t, and then plus I mean 0.36. And if you simplify this, you find that the inductor current is equal to 307, okay, 200 t plus 0.36. And this one is valid for, so it's amps, of course, an equation. It's a linear equation. As you can see, there's a linear relationship from the time t less or equal to d times t. And what is d times t? So you can calculate that. So d times t, so we know the duty cycle, we know the period. Okay, so let's try to calculate that so that we have the actual time. Okay, so how much is that? Anyway, you can actually just plug in duty cycle is 0.375, and then t period is 1 over frequency, right? 40,000. So I don't know how much is that. I haven't calculated. Let me just try. The calculator here. Okay. So 0.375 times 1 over 40,000. Okay, so that is about 93.75, or say 9.375 microseconds. Okay, so you can say this is divided between 0 to 9.375 microseconds. Okay, so that current, you have that inductor current. Now, what of between dt and the period, right? So let's also figure out. So the equation for this, okay, is given by, okay, so the equation for that is actually given by the following, which is IL of t is equal to negative VO over L, okay, times t minus c dt, okay, plus I max, right? Okay, so you know that dt, or duty cycle times time period, VO is output voltage, I max, okay, so how do we find I max? So first of all, we find I max. So I max simply VO 1 minus R, okay, plus 1 minus D over 2L times frequency, right? Okay, so I max, the output voltage is 18 volts, 1 over 10 ohm resistor plus 1 minus duty cycle, which is 3.75. Okay, divided by 2 times inductance, which is 97.565 microhenry, of course, and then times 40,000 hertz, right? And if you calculate this, you get that the maximum current is about 3.2 amps, I think. Yeah, 3.2 amps, 24 amps. Okay. All right. And then now we can go back to our formula. Okay. IL of T is equal to negative V output 18 divided by inductance, which is 97.565 times 10 to the power negative 6 is the micro, right? T minus D times T, okay, D times T is actually this period here, we found 9.375 seconds, okay, microseconds, which is about 0.0000097, is it right? 9375, okay, 9375 plus I max, right? I max is 3.24. So if you simplify this, okay, if you simplify it, you get the current of about negative 184.320 plus 4.968 amps, right? Okay, so this one is variable in dt. Okay, so dt, remember that it's 9.375 microamps or microseconds, less or equal to t, less or equal to time period, 1 over frequency. So what is time period? Okay, 1 divided by frequency. Okay, so that is about equal to 1 divided by 40,000. Okay, we're getting about 0.0025. Okay, so this is 25 microseconds. Okay, so 25 microseconds, that's the total time period. Okay, so this current will be divided between this time period, right? Okay, so you can actually try to check. Okay, okay, just try to check. So for this one here, if you put time is equal to d times t, okay, okay, in this equation, put time is equal to d times t, what you're going to find is that you're going to solve for the minimum current, okay. So the minimum current for the maximum current, of course, you get 3.24 if you substitute d times t here, okay. And then if you substitute t here, okay, for the after time period, remember that after one period, the current goes back to minimum, right? Okay, so if you put t here, okay, which is 25 microsecond in this equation, you should be able to get the minimum current, which is what? 0.32, isn't it? Okay, should be able, or 36, sorry. So you should be able to get 0.36 amps. Okay, similarly in the previous equation here, okay, where is the first equation? This equation here, okay, if you put d times t, remember that this equation is divided between d times t. Okay, if you put a 0, of course, you get the minimum current. This at time equal to 0. If you put d times t, then you have maximum current. So you should be able to get maximum current if you substitute d times t here. And d times t is simply 9.375 microsecond. Substituting this equation here, you should be able to get the maximum current, okay, of the inductor, which is 3.24. Okay, so you can prove those. So those are the inductor current that we're asked to calculate. Okay. What else? So we also need to select C so that the peak-to-peak output ripple voltage does not exceed 0.5% if L is equal to that and frequency equal to that. Okay, so this one here is also straightforward. We just need to use the formula. Okay, okay, so this part is D. I don't know if it's part D or part C. Okay, so for this one, we have just have to use the formula, and the formula is given by the ripple voltage. Okay, if you remember the first example that we solved, the ripple voltage is equal to VO, okay, 1 minus D divided by 8L CF squared, right? Okay. So remember that we are told that this guy here over V naught is 0. Okay, should not exceed this, should be less or equal to, right? Less or equal to 0.5%, right? Okay, so we can say the minimum, right? Okay, or the maximum, right? The maximum. So this delta, okay, sorry, delta V naught over V naught, okay, when it is equal to 0.5%, how it's going to be? So 0.5% is simply 0.5 divided by 100, right? So you have 0.005, right? Okay. And this is equal to, so I've just divided this. Delta V naught divided by that, right? So this side I'm just remaining with 1 minus duty cycle over 8L CF squared, right? Okay, so I'm solving for F, of course. Oh, sorry, I'm solving for C. So the capacitance is equal to 1 minus duty cycle divided by 8L, okay, F squared times 0.005, right? Okay, so if you substitute, the value is 1 minus duty cycle, which is 0.375, divided by the inductance, which is 97.565 microhenry times 10 power negative 6. Okay, times frequency, which is 40,000 hertz. Remember that we are squaring this times 0.0005. Okay, if you substitute everything, you'll be able to get the capacitance value. Okay, the capacitance value of 0.1 millifarads, right? Okay, so this is a capacitance value that we need to use. Okay, 0.1 millifarads. Okay, and then the last part of the question, says we need to find what? So the last part of the question, we have to calculate the minimum switching frequency. Okay, the minimum switching frequency. Okay, so again, that one requires the formula, of course. Okay, so that is I don't know, part E. So the minimum switching frequency fmin simply equal to R1 minus D, right? Okay, divided by 2L. Okay, twice inductance. Okay, also we can also be asked to find the minimum period, right? Or maximum period, sorry. So this will be 2L over R1 minus D, which is the inverse of frequency, isn't it? That is period. Okay. So this will be T max. Okay. So F min. Okay, so F min will just be equal to R is 10, duty cycle 0.375, 2 times the inductance 97.565 times 10 to the power negative 6. So F min, so minimum frequency is just equal to say 2 kilohertz. Okay, you have the 2 kilohertz here. So what it means here, the minimum we can switch this. Okay, this can be operating the switch or the transistor. This minimum frequency must be the 2 kilohertz, because remember that we're trying to have continuous current in the circuit. Okay, so we have to make sure that the frequency is high. Okay, we need to make sure that we are switching our switch at very high speed. Okay, yeah, so that we have continuous current in the circuit. Any frequency below this, then we're going to have discontinuities in the circuit in terms of current. Okay, yeah. So it means the frequency must be high or having a very, very, very small period, right? So no wonder we're saying maximum period. Don't exceed this, right? Yeah, having a small period, high frequency. Remember the waveforms, right? If you have a waveform that looks like this, okay, okay, this it looks like this. This one here, so just sinusoidal from pi here to pi, right? You see that? Okay, so in this from pi, from 0 to 2 pi, there's just one waveform, right? But now, what if no, this is not part of the discussion. Okay, what if we increase? So that one, now you see that in half a period now, we have 2 periods, right? Okay, so you notice that in half a period we have 2 periods. So now this now becomes what? Sine 2x, isn't it? Okay, the frequency has increased, isn't it? So we've increased the frequency here. So that's what it means, a high frequency. So if again we increase more here in just one half period, you have a lot of them, okay, then this one has high frequency. Let's say that, right? Okay, has high frequency. Okay, so this is a pi here, then you have let's say 2 pi at this point and all that. Okay, so this is a high frequency. Okay, so we need to make sure that the period is so small, but the frequency is as high as possible. No frequency less than 32 kilohertz if you want to continuous current in the circuit. All right, so we end here. Okay, and just wait for more videos come. Okay, I'll keep posting different examples in power electronics. So just make sure that you check all the times so that you are not left behind. Okay, thank you so much and have a blessed day. Okay.